That's great. Okay, well, hello everyone, and a very warm welcome to this second NoVOC Charge and Connect virtual coffee chat. It's the second out of currently 5 planned virtual meetups. Maybe some of you have already been at the first one 2 weeks ago. This one is the second, and I will repeat a little bit a few things that I shared last time. So for those of you who are here for the first time, already also know what we're doing here and what is planned. So what we want to actually reach with these coffee chats is to create a very informal and interactive virtual platform for knowledge exchange and discussion around the latest scientific and technological developments in sustainable lithium-ion battery manufacturing. My name is Nicole Schmidt. I am the communications manager of the NoVOC project. I will be your host of today. And together with my colleagues from our coordinating entity in Sweden, RISE, we set up this event together. So these events, these parts of the webinar series, they always look the same. So it's always 1 hour. So the agenda is each and every time the same way. We start with a quick welcome and introduction, and then there will be a 25 minutes keynote from our designated speaker of the respective event, which will be followed by a quick breakout session for an informal exchange where you can engage with your colleagues and other experts in the field. And then we will follow this by a question and answer session. The questions we will already collect via chat during the presentation. And at the end of it, I will give you a quick teaser for the next webinar and coffee chat that will take place in 2 weeks from now. Just quick information to start with. This webinar, as you have most likely heard, will be recorded, but just the presentation part, and it will then be uploaded to the NoVOC YouTube channel, where you can also follow up on it and maybe also share it with further colleagues. Those of you who have not yet renamed themselves, please do so, particularly for later in the breakout session, that people know who you are. You can do so via hovering over your video, and then there are 3 little dots, and there you can click on rename and just change your name to first name and institution. We also would like to invite you to turn your camera on, especially during the breakouts. Of course, you will be in small breakouts so that people actually see who they are talking to, and also during the question and answer session. And of course, if you want to, like some of us already have, also during the presentation, because as a speaker, it's also always nice to actually see some people and not speak into the dark void. Please stay muted when not speaking. And as I mentioned before, you can post questions for the question and answer session during in the chat already during the presentation. And we will then take them after the breakouts during the question and answer session. Of course, you can also always ask verbal questions. Then I would just like to invite you during the question and answer session to simply raise your virtual hand, and I will give the floor to you. So that brings me already to today's speaker, today's keynote. Today we have Stefan Gerl with us from Maschinenfabrik Gustav Eirich in Germany. And I want to quickly introduce him to you so that those of you who don't know him yet know a little bit more about him. Stefan is an engineer with a doctorate in mechanical process engineering and has over 35 years of experience in powder technology. And he says about himself that he's passionate about revolutionizing traditional production processes. And for that, he brings along an extensive knowledge of Eirich mixers and production processes from a wide range of industries. So we're very happy and grateful to have him with us today. And he will be speaking, but of course, about sustainable electrode manufacturing with a focus on aqueous and dry processing with intensive mixers. And that was it already from my end. So I will stop my screen share here. I'll just quickly check, no, everything here. And then I will give the floor to Stefan for his talk.
Nicole, thank you very much for your kind introduction. I welcome all my listeners to this afternoon coffee session I hope everyone has a coffee. I don't have because I have to speak now. I will talk about, let's say, use of Eirich intensive mixers in battery production for lithium-ion batteries. First of all, I will give a short introduction about the company Eirich. The company Eirich is a family-owned business, 161 years old. So last year we had 160th anniversary. We are now in 5th generation. So on the upper left picture, you see the founder, Gustav Eirich, who gave the name to the company. The 4th generation, Hubert Eirich and Paul Eirich. And then the 5th generation, Stefan Gerl and Ralf Roman, who is son-in-law of Hubert Eirich. We have here in Hartheim in Germany 530 employees worldwide as a group with 1,100 and a total turnover of 200 million euro. We have sister companies all around the world in the main markets like in China, Japan, the US, Brazil, India. For the first one was founded already 50 years ago. And even India is already now 25 years since its foundation. Eirich is a mixer supplier, but also plant engineering company. So we are not only producing machines, but we are producing complete technical solutions. And this includes raw material handling and weighing, then the mixing itself, and last but not least, also the control system, which is then the brain of the system. And we are dealing in the battery business since decades. Eirich is a world leader in lead acid battery preparation. We developed the so-called EVAC process in the in the late 80s, and this was somehow transferred to the lithium-ion battery industry. Our mixers you can find in raw material processing, like in cathode raw material for precursor mixing. You can find it in cathode material functionalization, where the coating the active material with nanoparticles, in anode raw material preparation for making synthetic graphites, also for silicon carbide composites. But today we want to talk about electrode mixing for the classical wet processing route for coating slurry, and the, let's say, somehow new processing route for dry electrode preparation. Eirich invented the planetary mixer, which is today's standard in the battery industry for wet application, in 1907. And in 1924, we invented the so-called Eirich mixer with a rotating mixing chamber and eccentrically mounted mixing tool. And this principle was so superior against the planetary mixer that we stopped at this time manufacturing any other kind than the Eirich mixer. So the only and solely product or mixer from Eirich is the so-called Eirich mixer, and this principle is already 100 years old and is still absolutely on top because, of course, it was developed in, let's say, many, many details, but the basic principle is the same. How does it work? As I mentioned, sorry. We have a rotating mixing chamber, which is doing the transportation of the material. By this, you can separate transportation and material mixing. If you have a planetary mixer and a static chamber, the tool has to do two things. First of all, the transportation of the material, and secondly, the mixing itself. If you increase the speed for increasing or to improve the dispersion state, then the material will be essentially fudged to the outside, and in the worst case, the material movement collapses completely. And by the rotating mixing chamber, now the tool can work independently. This tool is mounted eccentrically with a diameter of about 50% of the diameter of the chamber, and this is the same whether you go for a very small machine or whether if you go for a very large machine. And this allows us to scale up easily because the machines are geometrically identical whether you go for small or for large. The tip speeds typically operate in the range of 1 to 20 meters for wet application. Sometimes for LFP, we go even a little bit higher, but also for the dry battery electrode, we can run the machines of up to 45 meters per second tip speed. Whether this is always necessary, This has to be answered then by the customer, because this also has, let's say, the problem of causing additional wear. And we see that it is not necessary to go to this high speed, but the machines can do so. Thirdly, we have a static wall and bottom scraper. For the battery application, we made it really scraping. Beforehand, it was always on distance. We came from horizontal machines in the origin. Then in the 70s, they started to incline the machine to improve granulation and discharge. And for the battery industry, we moved back to horizontal because, first of all, the slurry will not flow up the hill. And secondly, the cohesiveness of these ultra-fine particles are causing wavy movement inside of the machine. And to challenge this, it's better to, let's say, put the machine horizontal again. We introduced some years ago the double jacket cooling system. Beforehand, we was never forced to do double jacket cooling because our process is so efficient that typically cooling via the walls was never necessary, or we do it in a different way by evaporation cooling, like in the lead acid battery industry. But today also we have mixtures available with double jacket cooling all along the bottom and the wall of the mixing chamber. We have additionally a pressure-resistant casing around the machine, which is helpful for the slurry application, where we can then degas in parallel to the mixing process. Typically, we have a discharge gate in the center of the mixing chamber, but this is now, let's say, covered by the cooling system. So we had to invent new discharge systems, and today we are sucking out the slurry, also the dry battery electrode material, via the hollow wall scraper of the mixer. For the slurry application, we additionally have high-pressure liquid injection systems, which allows us to add liquid with up to 100 bar, washing away adhesions of the material. So we can use it, of course, as a cleaning cycle or cleaning for washing out the machine, but also we add the liquid we have to add anyway in slurry preparation. We had these high-pressure systems to wash down all adhesions and to make sure that 100% of the solid is also part of the slurry. When we started this business, we said, okay, we can do it exactly the same way like a planetary mixer, maybe prepare binder solution, add the powders in the sequence and make the slurry out of it with no benefit for the customer. And we came then with a solution which is very popular already in the 60s in ceramic industry. So we add all powders from the very beginning. This includes the active material, the conductive carbon, but also the binder. And the binder is then dry mixed together with the active material for about a minute, separating the single particles. And then we are adding a first portion of liquid to make a plastic body out of the mix that we can intensively knead it and disperse the active material, the conductive material, but also solve the binder during the step. This takes roughly 7 to 8 minutes. And then we are just adding the missing liquid to make then the dilution to the desired solid content or viscosity. If we go in for an anode material, we're adding SBR at the final step, like adding cream into coffee, and then already the slurry is finished. And this, sorry, this is, so the slurry is finished after about 15 to 20 minutes. The advantage is that in every step you can individually adapt the parameters. You can change the times, you can change the speed and the shear rate by this, and so optimize the product, the preparation process. Additionally, as our tool doesn't touch neither wall nor bottom, we can also measure inline the viscosity inside of the machine by running the tool at defined speeds. When we have measured before the idle power, we can then measure the net power, and by this representing the viscosity of the slurry. It's like a viscometer in the lab. We can do this as a last step. We can do it before adding the final portion of liquid so that you can adapt the viscosity according to the needs. In practice, we know by experience that in gigascale factories, it's not necessary to optimize the production process. Typically, we have two kinds of machines: a non-vacuum machine, the vacuum machine. Of course, with a vacuum machine, you can also run non-vacuum. So then you would, and we call this machine a mix solver. And at the end, you have to degas. So we are transferring the slurry into a tank, and then we can do the degassing. If you have the vacuum machine, we are applying vacuum already during the first liquid addition to make sure that the complete process is running under vacuum. And by this, you have a properly degassed slurry at the final end without prolonging the mixing time. This is now a view or look into a full-scale mixer, a 500-liter R12 mixer with a, let's say, anode slurry you see running through the different phases of the kneading phase, seeing the change of material behavior within minutes. So, and already after about 7 to 8 minutes, you have the final, let's say, dough-like material flowing inside of the machine. And then we are just adding the missing liquid. And you see this even within, let's say, a few seconds, the material will, or the liquid will be incorporated completely into the slurry. And by this, you can easily achieve the final viscosity with additional 1 or 2 minutes of liquid addition. At the final end, we are sucking out the slurry by under pressure. And then to make the machine empty, we are, let's say, spinning the tools, throwing away all adhesions from the wall. And then at the end, you end up with a material or with a machine which is almost completely clean, just having some small, let's say, sticky layer of material on the surface of the tools. But this is, by experience, not a problem for going on into a production scale. What are the problems in the PD mixer? Typically, you see the PD mixer is not capable to clean the rotating planetary gear. We have typically strong adhesions on the rotor shafts of the DESPA tools with like needle-like structures which can fall apart and contaminate the slurry. And when the material caking becomes stronger and stronger, the let's say PD mixer has to be stopped, interrupted, cleaned manually, like with hard work. If you go with the Eirich mixer with a high pressure liquid injection system, we can clean all adhesions from, let's say, non-rotating parts in a way that we have a stable situation all along the mixing time and can go on by this batch by batch without interruption for a very long period of time in comparison to the planetary mixers. The mixer itself is incorporated, of course, into a complete, let's say, plant layout. This is having the, let's say, powder handling, typically coming from big bags or sacks, where you can go with barcode or QR code readers to identify the material properties correctly. Then we are weighing out the material directly into the mixer, or we are collecting it into an intermediate balance, which allows us to, let's say, run a dosing process in parallel to the mixing process, so that while one batch is running, let's say, in the mixer, you can already prepare the next batch so that the charging will take just 1 or 2 minutes to charge the complete filled, let's say, hopper into the machine. We are adding then the liquids from, let's say, liquid supply line.
Oh, here's back.
And the final SBR, then we are mixing. We can monitor the data like motor power, temperature. We can apply cooling. And at the final end, we are sucking the slurry by under pressure into a first, we call it qualification tank with the same volume like the mixer. You can take a sample, you can analyze it in the lab with your traditional methods, and then you are pumping it into a mobile tank, or like shown here, we call it Conti feeder, into a series of tanks with different volumes so that you have a buffer. You're collecting several batches, and then from the buffer, it is transferred directly by direct piping to the coating line. So this means you have, on one hand, let's say, a batch process. On the other hand, this is the most interesting thing for the operator. You have a continuous stream of qualified slurry to the coating line. All this is monitored by a control system, where you see the trend curves as, let's say, the eyes of the operator. And then you have the, let's say, different versions of qualification systems. First of all, you can, of course, measure the traditional data out of the machine. You can also add some additional sensors like viscosity sensors and particle size to qualify inline the complete batch. This is an example of a, let's say, SAT of a gigafactory in Asia. where the customer was running 10 consecutive 420-liter batches of anode material. And we see that the system is capable to run in a very, let's say, low tolerance or small tolerance band. We have very low standard deviations for the solid content coming from the dosing system, but also from the high pressure liquid injection. Constant solid content means you have constant slurry density, and of course you have also then constant viscosity. When we compare ourselves with alternative technologies like the PD mixer and the extruder, then you see that, of course, we can run, because of the short mixing time, we can have a much higher, let's say, output per volume like the PD mixer. And this is shown here. So you have a certain throughput rate on the retention time. In the PD mixer, you have typically, let's say, 4 to 6 hours mixing time. And even a 2,000-liter PD mixer has just an output then of about 200 liter per hour of final slurry, because these machines are already only filled with about 70%. If we have a 500-liter Eirich mixer, you can fill 500 liter of qualified slurry, so that the water volume of the machine is much bigger. And on the other hand, you have then the extruders, which has, let's say retention time between 1 and 10 minutes. The benefit of the Eirich mixer is that you have a wide field of application where you can change parameters like the filling level without changing the properties of the slurry, so that you can produce slurry or qualified slurry within, let's say, just-in-time production. Another important point is if you compare them with, let's say, energy consumption. In 1500, the PD mixer is equipped with roughly 300 kW installed power, 132 kilowatt main drive and a 160 kilowatt despot drive, has a mixing time of 6 hours. So it ends up with a roughly 500 watt hour per liter. On the other hand, you have extruder, let's say published values are laying in the range of 160 watt hours per liter or 85 kilowatt per ton. And the Eirich mixer was shown in many applications, many customer sites. We have roughly, let's say, energy consumption of about 20 watt hour per liter. This means we are 95% lower in comparison to the traditional PD mixer. And this is at the end the benefit for the customer also in operation, that he can save significant amounts of money. We have compared this here on an example of a 3,000 liter per hour 15 gigawatt hour plant. So the, let's say, anode capacity is about 2,950 liter, cathode typically a little bit less. And you see then the energy costs and the CO2 emissions. For the PD mixer, we have roughly 45 gigawatt hour in total electricity, because you have, let's say, 20 gigawatt hour for the mixing itself for a year. And additionally, you have then the chiller, the cooling water, which has to be supplied to take out the complete heat you're dissipating from the mixer. And if you compare this with the PT mixers, with the twin screw extruder inline dispersal, they have already significantly lower values, but the lowest values, because of this high efficient process, is coming from the mixolver. And sorry, this Zoom first time behaves differently to Teams. You have a significant saving of roughly 7 million euro per year, if you also include the CO2 certificates here within Europe. This is an example of a factory running in the UK, the UK BIC facility, with a 400 liter R12 mixer. At this time, it was a non-vacuum machine with the powder handling and dosing, liquid dosing, and the mobile transfer tanks. And then on the first floor, you have a sack dumping station, big bag dumping station, glove boxes for the carcinogenic active material. So it's an automated unit, which allows them to operate the machine like in a full-scale production. Of course, they typically just run 1 or 2 batches a week because of the high cost of the raw material for their customers. But in general, you can run this plant batch by batch without interruption. This is the concept, or latest concept for a gigafactory. with a capacity of about 10 to 16 gigawatt hour, depending on NCM or LFP, let's say cathode. For an NCM cathode, we are roughly on 16 gigawatt hour. This means we're running 4 machines per polarity on the cathode side, 4 machines on the anode side, 4 machines. They are all connected with one powder handling and dosing system. This is all the green one here, where you're weighing out the batches individually for every of these 4 mixers. Every mixer is equipped in a modular way with a pump skid and a tank skid. So this is a, let's say, unit which can be pre-configured, can pre-assembled and pre-wired, so that the startup sequence is quite fast. In comparison to the traditional PD mixers, you see the height or the distance difference in the size of the equipment. This is a typical 1500 liter PD mixer with a height of about 6 meters. And in contrast to this, the Eirich R12, which is a little bit higher than a typical, let's say, person. And at the end, you're also ending up with significantly less footprint. And this is beside of the cost for the equipment, you have significant savings and also in the building and dry room, for example. Now changing from wet to dry. So with the same mixer, and this is a capability of the Eirich, you can do dry mixing, you can do granulation, you can make slurries, pastes, whatever. We can run with exactly the same machine also dry electrode mixes. The target is, of course, here to get rid of all this yellow equipment for dry battery electrode, the coater, the dryer, the exhaust air treatment, solvent recovery, and tank systems. But you have to have in mind, additionally, if you go for PTFE as a binder, for example, you need, let's say, temperature control, and you need new solutions for powder transfer and dosing between the mixer and the calender. And you have to take care and have, let's say, solutions for the recycling of the return material. While in coating, you have always, let's say, a proper electrode. In film formation, you have to make the film, to have to cut the edges, trim the edges, and then you have to return this material into the process. Otherwise, the yield will be too low to be efficient. What are the challenges to make a thin film? It's not a problem to make a thick film. It's a problem to make a 50 microns film for NCM material with absolutely uniform, let's say, dimensions across the widths and the lengths. We have to go for wide electrode films because otherwise you will never be competitive to, let's say, wet application. You have to face the challenge with abrasion while the liquid is, let's say, reducing the wear. You have significant higher speeds and you have direct contact of the product like NCM or silicon oxides, which are produced in iron intake and reduce the lifetime of the tools. And of course, the iron is very negative in the battery performance. You have to handle the binder in contrast to the ultra-fine materials like LFP. We have to, let's say, find solution for the handling and storage of fibrillating PTFE. And of course, with all these transfer between mixer and calender, as well as the film edges. With the Eirich mixer, you can go 3 different routes. One is, of course, adding all additives or, let's say, all components at the same time, like active, carbon, and polymer. Mix it together. It is possible, but typically the PTFE grabs the fines, like the carbon, coats himself with the carbon, and by this, the fibrillation is, let's say, limited. Alternatively, you can mix the active and the binder first, make the fibrillation, and could then add the carbon. Then the carbon will be not properly dispersed and will, let's say, sit on top of the fibers. But this is a typical way of application when we go for anode, which is not containing carbon. But the preferred route is to coat the active first with the carbon, add then the PTFE on the carbon, fibrillate the mix, and then make the dry electrode. How does it look like in reality? So we have the cathode active material with a high bulk density and the small amount of conductive carbon with a very low bulk density. We mix it when we run not long enough or not intense enough, then you see by taking a sample and tapping the sample that it will separate. The carbon will float on top. And if you go on with, let's say, reasonable speed and time, you see that after a certain period of time, it completely disappears. So that you have, let's say, the carbon completely incorporated into the powder mix. This mixing time is roughly 10 to 15 minutes, depending on the speed. And how does it look like in detail? If we have here a look into the SEM pictures, you see in the beginning, after, let's say, starting, still clusters of the non-dispersed carbon black. With ongoing mixing time, the carbon black clusters become smaller and attach on the surface of the active material. So after 4 minutes, all, let's say, free carbon is almost, let's say, disappeared, and all the carbon is sitting on the surface. But you see also with ongoing mixing time that the structure of the particles changing of the active materials, and the coating becomes even better with the time. So by this, you can see that there's a coating process superposed by the mixing process, and you can design your particle and the particle structure inside of the final electrode. Then we are adding the PTFE. We mix it at low speed just to have a homogeneous powder mix. This could be already the powder which can be applied for an electrode making. Instead of PTFE, it could be, for example, PVDF to make then a spray coated or a 3D printed electrode. If we have PTFE, we increase then the shear rate. We increase the temperature by shear. And only a question of time, you have then, let's say, a full plastic body without containing any liquid. And you could imagine that this can be easily transferred and rolled out into the film. This material is hardly to handle into a calendar, so this is why we are cooling the mix. We are chopping the mix into small granules. And the target is then to have a conveyable, free-flowing powder mix to fill then the calendar gap to make then the free electrode film out of it. This is then showing a result. We was participating in the ProLab research project together with the MEAT and the EPAT and companies like Saueressig. So on the right-hand side, you see a cathode film produced in this process. On the left side, you see the calendar film in SEN picture. The fibrillated mix out of the machine must be not 100% fibrillated. The fibrillation is part and also of the coloring process. Yes, you need a good pre-fibrillated material and a stable material which is not segregating during the handling and the processing. And at the end, we always see that, or in many cases, we see that the performance of the dry battery electrode is superior to the traditional wet electrode. So coming to an end, I will show you, let's say, we have seen one of our largest mixer for the battery electrode, the 500-liter vacuum machine. On the other hand, we have now the 100 milliliter EL1 Nano, which is also capable to make slurry or dry battery electrode material. This allows you to make then coin cell development in the smaller scale, not to waste too much raw materials. As I mentioned, basically exactly the same geometry. You can run the same speeds so that if you make the basic development on this machine, you can easily scale it up then to larger scale. This was done examined together with the KIT. It was doing tests with different sizes of machine at different parameters, and we could figure out that the bulk density, or let's say both processes can be shown in a dimensionless approach with a mixing index over the mixing tool rotation, that all data collected, like the bulk density over the mixing time, are running on one regression curve, so that you can see that the scale up is easily possible from the smaller machine to larger machines. This is then the view of the dry battery electrode in a full-scale machine, 500-liter mixer, where I was also preparing 300 liter of anode material for a customer. So basically exactly the same like shown before in the videos. You have the plastic material, you chop it by cooling, and then you have a free-flowing material for making your free electrode. There's then a plant of a, let's say, large-scale giga pilot facility, which is capable to do wet coating or wet slurry as well as dry electrode. Additionally, beside of the, let's say, powder handling and liquid for the traditional wet application, we have additionally PTFE dosing system, and we have a pneumatic extraction system for the final, let's say, dry battery electrode material. And this machine is capable of running up to 600 kg of NCM cathode material per hour. So thank you very much for listening. And I hope I could, let's say, cause your interest, and hope you will become also a pioneer in electrode processing. Thank you very much.
Last slide to share with you, giving you an outlook on what is going to happen in 2 weeks from now. We'll have our third Charge and Connect webinar just in 2 weeks, Monday, September 15, same time at 2 p.m. And this time we will have Yashari Granit from Fraunhofer IKTS speaking about solvent-reduced electrode manufacturing innovations in anode and cathode processing. If you have not yet registered and are interested, you can do so via the QR code. And of course, we will also again promote it on our LinkedIn channels and on our website. We will send out the YouTube recording of this event to you. So we will also include again the information about the next Charge and Connect. That's it also from my end. I hope it was interesting for you. I hope you'll be back next time. Have a lovely afternoon. And yeah, all the very best. Thank you for joining. Bye, everyone.
Thank you.
Thank you.
Thank you.